In this video, we're going to look at a sample AP Physics 2 question dealing with Unit 3 material, dealing with electric fields, and specifically here, it's going to be focusing on electric potentials, or lines of equal electric potential, which are otherwise known as isolines. So this is a publicly released free response question. So all this in red is things that I've written on here, which is going to aid in the explanation. So the black is essentially the diagram that's given. Let's read what it says. It says the dots in the figure above represent two identical spheres, x and y, that are fixed in place with their centers in the plane of the page. Both spheres are charged, and the charge on sphere y is positive right there. So I put a little positive sign there. The lines are isolines of electric potential. Remember, an isoline is of electric potential is a region in space, which is represented by a line, that's all at the same electric potential, also called equal potential lines, also in the plane of page, with a potential difference of 10 volts between each set of adjacent lines. So from this line to this line is a 10 volt difference, from this line to this line is a 10 volt difference, and so on. It says the absolute value of the electric potential of the outermost line is 50 volts. So I've just labeled 50 volts on the outside line there. First question asks us to indicate the values of the potentials, including the signs at the labeled points A and B. So we're looking for whether it's a positive or negative potential and what the value is at point A and point B. So if we come back up to our diagram, we're looking at point A and point B. So they just say the outside one is 50, and if we go to the next line, it's got to change by 10 volts, so it's going to either increase voltage or decrease voltage. Well, two things we have to remember to know whether it's going up to 60 or going down to 40. They told us that Y was a positive charge, and from that outside line to A, you're moving closer to a positive charge. You have to remember that electric potential, which is the amount of energy stored per unit coulomb, which is related to electric potential energy, that's going to increase as you get closer to a positive charge, because if we take a little positive charge out here, and we move that positive charge closer to another positive charge, it took a force to do that. We applied force in the same direction it moved. We're doing positive work on the particle, which means we're adding electric potential energy. And if a positively charged particle has more electric potential energy at point A than it does out here, that must mean it's at a higher electric potential. So at point A, it has to be 10 volts higher than this outside line. So this one's 60 volts, all along that line right here. The next one in is 70 volts, all along that line that goes over around both of the spheres. And we just keep going. So 70, 80, 90, and then the line closest to sphere Y is at 100 volts. And if this line out here is 70, and we go one in, that's 80 volts, another one in, that's 90 volts, and it's kind of hard, but I've got lines drawn here. The one on the inside is 100 volts. So the line closest to sphere X and the line that's drawn closest to sphere Y are both at a electric potential of 100 volts. But to answer the question, at point A, it's positive 60 volts, and at point B, it's at an electric potential of positive 80 volts. So positive 60 volts at A, and positive 80 volts at B. First part of part B says, how do the magnitudes and the signs of the charges of the spheres compare? So are they the same charge? Are they two positive charges? If Y is positive, is X positive, or is it negative? And which has more net charge at that location? And how do we know? Explain your answers and it doesn't just say explain your answers, it says specifically explain your answers in terms of the isolines of electric potential shown. So our evidence, whatever we say, our evidence has to come from making reference to these lines of equal potential, or the given electric potential lines. And so let's start with signs. We know that's positive, right? And so electric potential is going to be going down like this. And the question is this positive or is this negative? Well, like when we went out here, we knew this was 70 volts, and sorry, this line right here is 70 volts. And if we jump a line, we don't know, is that like going down? Is that going down to 60 or up to 80? Is that going, again, down to 50 or up to 90? So like technically you could go from this line to this line and you could be decreasing electric potential if that was a negative charge. And so I've added these lines on here because or these values on the lines because I've already thought about whether this is a positive charge or a negative charge. And if this is a positive charge, you know, from 70, and as we get closer, you have to increase in electric potential. Well, I was thinking, well, what if this was a negative charge? If you have, you know, a dipole, a positive charge and a negative charge, there will always be some line or curve in between those two charges that's at a zero electric potential, right? So like whether that's, you know, straight up and down, there's some line between those two charges. And there's no isoline or line of equal potential that kind of separates one charge from the other. Like this 70 volt electric potential line goes all the way around both of them. So there's nothing kind of coming in between there. So because there's no one line in between the two charges of equal potential, there can't be a line of zero electric potential between them, which means these cannot be opposite signs. They have to be the same sign charge. So if y is positive, x also has to be positive. And then the second question is, which one's a larger net charge? Well, notice if you put a little charge at this line, it's at an electric potential of 100 volts. That's really, you know, if we put a 1 coulomb charge there, that 1 coulomb of charge would have 100 joules of electric potential energy stored. Or if we put a 1 coulomb charge at that line at 100 volts, they would also store 100 joules. So which one must have more net charge, y or x? Or are they the same? Well, if you can get, if something stores 100 joules at a larger distance away from than another one, or this 100 volt line is farther away from y than it is x, that must mean that y has more net charge than sphere x does. Because if we place a positive charge here at this distance, or let's say we take a positive charge from an infinite distance away and we push it all the way close to here, it's going to give it some amount of electric potential energy. We don't have to get nearly as close to y because it's pushing with more electric force. That's another way to think about it as x. And so because the electric potential line of 100 volts is farther away than y compared to x, that means y must have more net charge. So the way that, I just kind of talked through it with the diagram, but the way that I would write it out would be the spheres have the same sign, because if one sphere was positive and the other negative, there would be a line of equal electric potential, or isoline, between the two spheres. There is no such isoline, so the charges must be the same sign, like we talked about before. And then what about the size of the amount of charge? Well, sphere y has a larger magnitude charge because there is a 100 volt electric potential farther away from it than sphere x. And I think that would be sufficient answer for answering those two questions. All right, the second part of part B. It says, the spheres at points x and y have masses in the same ratio as the magnitudes of their charges. The isolines of gravitational potential for the spheres have similar shapes to those of the isolines shown. Explain why the two sets of isolines have similar shapes. Well, if we go back to our diagram, this represents lines of equal electric potential, but remember, this could also represent something like a topographical map where these lines represent lines of equal gravitational potential, which translate into lines of equal height if you're talking about a topographical map or gravitational isolines. And so why, if you had a mass here and a mass here, why would these lines, why would they be shaped similarly if these represent lines of equal gravitational potential? So the way I'd answer that would be this. Two masses would similarly apply a force to a third mass in the region around both masses. Moving the third mass to a different position would require the addition or subtraction of gravitational potential energy, so the third mass would change gravitational potential and move to a different isoline. So we would expect to see different isolines around two masses. And since the ratios of the magnitudes of the masses are similar to the ratio of the size of the charges, like, we're saying since sphere Y has more charge, we're also saying that would represent, it would be an object with more mass. Also, so that's why we're saying, like, moving a mass around would change its gravitational potential energy, just like moving a charge around would change its electric potential energy. So we would have different gravitational potential lines, just like we have different electric potential lines. Also, masses are all positive. So the spheres / masses would produce gravitational isolines in a similar shape to the electric potential isolines created by either two positive charges, like we've described here, or two negative electric charges, right? The isoline map that we looked at were for two similarly charged particles, or charged objects, or spheres in this case, and masses are all positive. We don't have negative mass. As far as we know, conclusively in the universe, all masses are considered positive, so masses will be attractive to one another. So getting to the idea of the electric force and the gravitational force and whether they're the same or different, that's kind of what part C is asking about. It says, based on your answer to part B2, briefly describe one similarity and one difference between the electric and gravitational forces exerted on the proton by the system of the two spheres. The similarity and difference you describe must not be ones that generally apply to all forces. So, what generally applies to all forces? That, well, forces cause accelerations, or forces can do positive and negative work. Like, that's true for all forces. Like, we're kind of zeroing in on the similarities and differences specifically to the electric and gravitational forces. So what's a similarity of these two forces that's not true of all forces? Well, it's kind of this 1 over distance squared relationship, that the size of the force, whether it's the gravitational force or the electric force, is proportional to 1 over the square of the distance. Right? So that's the same between both of those forces when you're talking about the size of the electric force of the gravitational force between two objects. Well, what's different, right? That's the same. But what is different is, well, the two spheres, in our case, exert a repulsive electric force on the proton. If the two spheres are positively charged, they're going to push that proton away from that two-sphere system. Well, but how's that different than the gravitational force? Gravitational forces are only attractive, right? And the size, well, all masses attract one another gravitationally. Masses do not repel one another gravitationally. So, electric force is attractive. The electric force is repulsive. They push each other away. The gravitational force is attractive, and that is a difference. Part D says at some time after being released from rest, so being released, at some time after being released from rest at point B, the proton is moved through a potential difference of magnitude 20 volts. So they don't tell us whether the voltage went up by 20 volts or went down by 20 volts. It just says that's the amount of change, not the direction of change. Part 1 asks us to determine the change in electric potential energy of the proton sphere system when the proton is moved through the 20 volt potential difference, whether positive or negative. Express your answer symbolically in terms of Q, the charge on the proton, the electric potential at position A, the electric potential at position B, or Vc, the electric potential at position C, and physical constants as appropriate. So I redrew a little diagram of the situation. We're putting the positively charged particle, or the proton, at position B, and remember, it says it's released from rest. So what will a positively charged particle do at this position in space? Remember, it is next to a positively charged sphere, that's sphere Y, and so it's going to feel a repulsive force away from that positively charged object. So proton released from rest will naturally move from a high electric potential to a low electric potential, right? It's going to feel a force away from that positively charged particle. So it's going to move from the electric potential at B to the electric potential at A. Knowing that, we can use this AP Physics 2 equation that tells us how the electric potential energy will change if a system, if we multiply the charge that moves times the change in electric potential it moves through. So we know it moves through 20 volts, right? Positive or negative. Well, the delta V will technically, in this case, be negative. But we're expressing this just in terms of these given variables, and so we have to put this in symbolic form. So the charge is just Q. We just leave that alone. And what's the change in electric potential? Well, the change in any value is the final value minus the initial value. In the end, it reaches V sub A. In the beginning, it was at V sub B, so the change in electric potential will be the final electric potential, VA, minus the initial electric potential, which is VB. So this expression right here represents the change in electric potential energy of the proton sphere system as in the situation that they described to us. Second part of D says, as it moves through the 20-volt potential difference, the proton was displaced by a distance d by the electric force. Remember we said pushing the particle away from position B or away from Y. It says determine a symbolic expression for the total work done on the proton by the electric field in terms of the average magnitude, or E sub AVG, of the electric field over that distance. Well, we know that around a positive charge, there's there's electric field lines that point away from a positive charge. So this little proton will be at this spot with the electric field pointed up and to the right, and so it's going to feel electric force up and to the right. And that electric field is stronger close to the positive charge Y and gets weaker as you go through here. So as it moves farther away from charge Y, the electric field strength is decreasing in size, which means the electric force will decrease in size. And so they're saying, let's just say that when it goes from position B to position A, it is in an average electric field strength of this. So that way it just makes our expression quite a bit easier. So if we want to figure out the work done on a system, it's the external force applied on the system multiplied by the distance that it moves while feeling that force. And we can just multiply F times D as long as the force and the distance is parallel, right? Well, in this case it is. Like that's D, it's kind of in this line, and the force is in the same direction as the displacement. So there's positive work being done. So it's the work is equal to the force times the distance. And what's the external force the proton is feeling? It's the electric force. So it's just Fe times D. Well, we want to put it in terms of the average electric field strength. So what equation do we have that tells us how the electric field strength, how the size of the electric force that a particle feels is related to the electric field strength that it's in? Well, it's this one right here. Electric field strength is equal to the electric force divided by Q, or if we solve this equation for the electric force, we multiply each side by Q and we get that the electric force is just equal to Q times E. So the work done is equal to the force times the distance, or the charge times the average electric field strength times the distance. So here's an expression for the amount of work done, or the magnitude of the work done on the proton. All right, last part is getting us to think about the correctness or incorrectness of some statements about what's going on. So two students are discussing how and why the kinetic energy of the proton would change after it is released. Student 1 says that if the system is defined as the proton and the spheres, the increase in the proton's kinetic energy is due to a change in the system's potential energy as the proton moves through the 20-volt potential difference. Student 2 says that if the system is defined as only the proton, so it does not include the spheres, the kinetic energy of the proton increases because positive work is done on the proton by the electric field as the proton moves through the 20-volt potential difference. So it says discuss each student's claims, explaining why each is correct or incorrect. So it doesn't tell us what is correct or incorrect about that. We have to make that decision and explain why. So student number one. Student number one is correct that the proton spheres system, so the system including all of that, it increases kinetic energy as the system's potential energy decreases when it goes through an electric potential difference. That's basically what they said. Well, why is that true? When you define a system to include all involved objects in a situation, the system's total energy stays constant. If there's nothing else like acting on the system, there's no outside forces, there's no work being done, the total energy of the system has to stay constant. So, as one energy decreases, another must increase, so the system's total energy is conserved. So, as the electric potential energy went down, or as the kinetic energy went up, that was only because another energy within the system itself must have been going down. So as the electric potential energy went down, the kinetic energy went up in the system, all a part of the system. Turns out that student 2 is also correct when they said the proton gains kinetic energy through the positive work done by the electric force caused by the electric field. That's true because when a system is a single object, that object can only gain energy, in this case kinetic energy, when a force from outside the system is exerted on the system in the same direction the object is moving. And since it's in the electric field is causing this little positively charged particle to feel a force in the same direction it's moving. That's kind of what we talked about up here, and there's work being done. And so that means student number 2 is also correct.